Recording. All right, so we're going to look a little bit at piecewise defined functions today. Piecewise defined functions are pieces of functions all together on the same graph. So they'll have an f of x or g of x or whatever they're calling the function, and then you're going to have three different rules here that you're using, and they're going to tell you which part of each function you're going to keep because you're only keeping a piece. So for example, when you have 2, this would be like having y equals 2. It'd just be a horizontal line like this. Make sure you're doing this in pencil because we're going to draw and then we're going to erase. So this would be y equals 2. But they only want the part if x is less than or equal to negative 5. So I'm going to go to negative 5. 1, 2, 3, 4, 5. Those numbers are almost too small enough. And I'm just going to keep from here over and erase this. And once you get good at this, you might only draw the piece that you need. But in the beginning, you just want to graph the line and then take off pieces. So for the next one, we have x plus 6. So if you think slope-intercept, 6 is the intercept. 1, 2, 3, 4, 5, 6. And I've got x, so the slope is 1. So up 1, right 1, up 1, right 1. And so you could do quite a bit of a line here. So if we did the whole line, it would go out to your edges like that. We only want the part from negative 5 to 4. So what you do is you go down to your x-axis. Here's negative 5. So I need to make sure I have my points accurately. So I'm only going to down to negative 5, and then I'm going to go up to positive 4 where my last point is, and they just want that section. Where the symbol that's next to the negative 5 does not have an equal to, so instead of a regular point, we put a little circle that's not filled in. And on the other side, they do have an equal to bar, so you put a little endpoint on that end. So this is not filled in, this one is. And so that's the second section. And in the third section, we just have negative 1/2 x. So you could think of that as being plus 0. So we just start at 0, 0. Down 1 over 2, down 1 over 2, down 1 over 2. So you can think about, oh, that's going to be my line. They only want the part where x is greater than 4. So if I go to my x-axis where 4 is, go down to where the line is, they only want this part to the right. And I have to decide then if this is going to be an open point or if it's filled in or not. So what do you think?
No.
No, because there's no bar there. So at 4, I'm going to make this an open circle, connect it out this way, and I'm going to get rid of any points I used to start my line because I don't need anything back here at 0. We're just keeping part of the line. So basically, if you remember your slope-intercept form and you can graph lines, that's basically it, and then we use this to find pieces. Then they'll sometimes have little questions down here, like, what is f of 2? Well, in a normal function, you just put 2 into it and it's all good. With here, you have to figure out which part 2 is in. So if I go over to 2, and up here, it's at 2, 8. So, oh, that's going to be 8. And if it wants f of 1, I have to go to 1, go up to that part of the graph, and it is 7. If it wants 5, that's not on that middle piece. That goes over to the next piece. And it's down here a little ways, and we can't tell exactly what it is from the graph, but this is from that last equation, the negative 1/2 x. So I can quickly just take negative 1/2 of 5, and you end up with negative 2.5 or 2.5. You can kind of see that's about where it is right there. But it's hard to tell, so you can go ahead and use the equation. You just have to figure out which part of it you're using because it jumps around. So f of 4 is interesting because we end this bar at 4, and we start this one at 4, but only one of them counts. Which one counts?
That one.
That one, because it's filled in. So that's the one that we use. So that's all the way up at 10. So you will never have 2 filled in points above each other because if you did, then it wouldn't be a function. So they will typically make sure that one's filled in and one is not. All right, so negative 5, 1, 2, 3, 4, 5, is where this endpoint is. This one's not filled in, but this one is. So the one where it is filled in is the one that you keep. So that's going to be positive 2. And then on the next one, we have f of 2.75. So 2.75, we can kind of estimate it up here. It's between 8 and 9. But we actually want to use the equation if we are going to have anything accurate. So that's the middle piece, which is from my middle equation, x plus 6. So we're actually going to take 2.75 and add it to 6. And you get 8.75. So it's just pieces of functions that are all put on the same graph. Sorry, I was off the screen a little bit. So let's try to do another one of these. There's only 2 where we graph, 2 where we write the functions from the graph, and then a quick story problem. But the ones at the top take the longest because we're actually drawing. All right, so there's only 2 pieces of this one. A piecewise function can have as many pieces as it wants. I've seen some that have 25 or 30 different pieces on a giant graph. So this one says, so we have f of x equals negative 1/4 x plus 3. At first, I ignore this part. I mean, I can kind of look at it, okay, I'm between negative 4 and 4, that's good. But I just start by drawing my line. I start at 3, my slope's negative 1/4, so down 1 over 4, down 1 over 4. And I can go up 1, back 4, up 1, back 4. I don't want to go too far because they only want from negative 4 to positive 4. So really, I didn't need these outside points on either end at all. I just need to figure out what my endpoints look like and fill it in. So next to the negative 4, we have an equal to bar, so that one is filled in. Next to the positive 4, it does not have an equal bar, so I'm going to change that to be an open point that doesn't really count, and then connect that across. So that's my first piece, and then I've got to do my second piece. 3/4 x minus 1. So you start at negative 1, go up 1, 2, 3, over 1, 2, 3, 4. And so there's a point sort of in the middle of that, so I just kind of put a bullseye there and figure it out later. And then do another one up 1, 2, 3, over 1, 2, 3, 4. And let's see, they want the part where x is greater than or equal to 4, so they're wanting this right here. So we're starting the graph with a point that's filled in on top of a point that wasn't filled in. The filled in point trumps the one that wasn't filled in. So this part, because it's going to be filled in on this end, we go ahead and take that and fill it in. And these are going to be connected. And on this end, it's going to go off to infinity because you have that, it's just greater than. So this one stops, that one goes on forever. These are the types of graphs that you guys thought were really weird when we were doing domain and range. Like, I've never seen one that just zigzags around. This is how you get them, is you just take parts of graphs and put them together. So then if I'm doing f of negative 4 is up here at 4. F of 0 is right here, and that's 3. And then f of positive 4, we filled in this point using the second piece, and so that's at 2. And strangely enough, if you put 4 into either of these equations, you'll get that point. Since we ended up filling in a point that wasn't filled in, it actually is the point where those two lines cross. So that's an interesting piece. Okay, so we're going to flip it around and look at some that are already graphed and go backwards to write the function. It's not super bad if they're all lines. So if you have a horizontal line like this, that's going to just be a constant function. To start off with, you want to name it. Let's just use a generic f of x because I'm not feeling as creative right this moment. And then you make your big bracket just the best you can. I don't grade on your artwork. So this little piece is at a height of 3. So I'm just going to say the first one is just 3. Well, where is it 3? It's 3 from x is negative 4 to the left. So it's 3. You write the word if x is less than or equal to 4. So since that point's filled in, I did the equal to. For the next one, it is slanted, so we're going to have a slope and a y-intercept. So if we're doing slope, I can go from one endpoint to the other if I'm just not really sure about the in-between points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over 5. So 10 over 5 would be a slope of 2. So 2x, and then if I look, it does look like it goes up for 2, up 1, or up 2 over 1, up 2 over 1, up 2 over 1. And then it goes through the y-axis at 1, 2, 3, 4, 5, 6. So I put a plus 6. And that is if x is between this point and this point, and they're not filled in. So it's from -4 over to 1. We're using the numbers off the x-axis. So an easy way to do this is to put -4 and the x and the 1, and then just put some less than symbols in there. You're always going to use less than. They're always going to point to the left if you go from the left to the right. And then the last piece is this piece over here. The slope's pretty easy because it looks like it goes down 1, right 1, down 1, right 1, down 1, right 1. So it's a boring -1x or -x. And then we have to figure out where it would cross the y-axis even though it doesn't cross. So if you went up 1 and back 1, it would cross right here at 3. So we use +3 even though it doesn't actually touch 3 because that's what tells you how high the line is. It's kind of weird. And that's if x is greater than or equal to 1. So that's the answer, is just getting those 3 pieces. And typically how I grade these is I will give a point for each piece, and then I'm trying to think. Sometimes I give a point for each of these and also a point for each of these. Sometimes I split it in half and call this worth 3, but I do break it down. If you got the first 2 pieces right and the third one wrong, I don't count it all wrong. All right, let's do one more of those.
Wait, real quick.
Yes.
I was zoning out. Why
Yes.
is it +3?
Because if this line were extended out, that's where it would hit.
And then why is the x more than or equal?
Because this point, it's from x equals 1 to the right. So see how it's from here over?
Oh, so even if it's
So if it goes
down.
right, then it's greater.
Yeah, if it's going to the right, well, yes.
Okay.
So you use less than for these ones where it's between, but since this one is greater than, sorry. I've often wondered why we couldn't just use interval notation for this and go, well, from -infinity to 4, but nobody does it. I'm not super sure why. They always go back to these old-fashioned inequalities. I think interval notation would be easier, but I don't get to write the books. I guess I could. I could write a textbook. I don't know. Make a little extra money.
Do it.
Use up my boring summers off. All right, so this next one has a couple of horizontal pieces. I think those are the best because they're just a number. You just have to tell how high they are. So this first piece is just at 3. And that's if x, so it's from -5 to the left, so x is less than or equal to -5 because that's filled in, goes to the left. Does that make sense?
Yeah.
It's kind of like what we used to do on the number lines where you would fill it in or not fill it in, right or left. It's just that we're sort of 3-dimensional with it here. And so this next piece is up here at 5, so the height of 5 is what goes here. And that's when x is between -5 and +1. So I always put the -5 on the left, the +1 on the right, the x in the middle, and then I fill in my signs. So this is not a filled in circle, so I just put a less than. This one is filled in, so less than or equal to. So when you're doing that between thing, just go from left to right, use less thans, decide if it's equal or not. And then this last one's a little bit tougher because we have to figure out where it would cross the x-axis. So we have to have a pretty good idea of the slope. So let's do the slope first. It looks to me like it's going up 2 over 3, up 2 over 3, so 2/3 x. So it's right here. If I'm going back just 1 unit to the left, instead of going back 3, because it was 2 units for every 3, if I'm going back 1, that means it's going to drop 2/3, because that's your slope for every unit. It's dropping 2/3 to the left. So this would be like 4 1/3, which is a little tricky. And then that is if x is greater than or equal to 1. And if you can't, or having trouble figuring out exactly where this crosses, there's some algebraic things that we can do that we'll maybe talk about in the next lesson since we're running short on time. This next one we're just going to cruise through. I've got about 7 minutes of class, so I'm just going to try to get through this, and then we'll expand upon this idea next week. So this is probably a really old problem. I don't know if data still looks like this, but whatever. My new cell phone has the following charges for data per month. Write a piecewise function that gives the monthly charges for different amounts of data usage, then graph the function. So data usage under 3 gigabytes is free. I don't know if I've ever seen any where data was free, but maybe this is a really good deal. Data usage from 3 kilobytes to 5 kilobytes is $10. Anything over 5 kilobytes is $20. I think they actually do some different things with that now, but we'll just pretend that's how it works. So if I'm going to write my function, I might use C for charges. And then my X would be the kilobytes that I'm actually using. So if I'm under 3 kilobytes, it's free. So that means I'm going to pay $0 if X is under 3. Does that make sense? And then it's $10 if it's between 3 and 5. So 3 is less than or equal to X is less than or equal to 5. And then it's $20 if X is greater than 5. And I should have drawn that a little smaller, but I'm just going to put a little graph over here to the side and we'll make it fit. So I'm just going to draw a really quick sketch of a graph rather than grabbing graph paper. X is my kilobytes and Y is my money, my charges. I'm just going to put dollar signs up there to label that. And so we don't have to make this super, we can just say, okay, $10, $20. We'll go just a little past the graph, $30. And then over here for kilobytes, I need to make sure I'm at least going up to 5. So 1, 2, 3, 4, 5. Maybe go a little past. We'll go to 6. So these are just going to be horizontal lines. So from 0 kilobytes up to 3 kilobytes, it's free. We're going to be down here at 0. So I'm going to have a point here, and then I'm going to have an open circle at 3, because as soon as I use 3 kilobytes, it jumps up to $10. So I'm going to have a bar from at $10 from 3 to 5 kilobytes. And then anything over 5 is 20, so I'm going to do a little open dot there. It has to actually top out over 5 to go this way. And this is called a step function because it just sort of looks like stair steps. They can't actually connect them vertically because then it wouldn't pass the vertical line test. 3 minutes to spare. We did good.